Okay, so maybe we can start. So last talk of this week, we're talking codes, is by Sarah, and there are many instances in quantum field theories where BPS quantities turn out to be some Q expansions. There are many interesting Q series in low-dimensional topology. Sometimes they're related, sometimes not. But quite often, in either case, they exhibit some modular properties. So that's, I think, general theme, and more specific title is one of our floor is yours.
All right, thank you. That was a great beginning motivation by Sergey. So what I'm going to try to do in the talk is mostly focus on this, because I think a lot of the people in our program are physicists, gauge theorists, or topologists, and maybe haven't seen or don't know in depth so much of some of the objects from number theory that I want to talk about. So I'm hoping that I can bring, well, and that's what I know most about, I guess, so I'm hoping that I can bring that kind of perspective. And so I'm going to say things which are hopefully pretty basic, but maybe you'll get something that you didn't know before out of it, and try and answer questions along the way. But before I do that, I just want to start with a very broad kind of motivation for what I'm going to talk about and why you, as an attendee at this workshop or at the Chaos workshop, might be interested in hearing what I have to say. So the general idea, is this big enough? Yeah. Okay. So the idea, I've never used a board this large before, so it's kind of intimidating. It's just study certain questions which naturally arise in a variety of areas in physics or math. So the idea is that we have a number of natural questions from several places, and the ones that I'm going to mention are topology, physics, very specialized questions in physics, I guess, but of interest to people in this workshop, and number theory. And it turns out that many of the objects that start popping up when you start attacking these questions are the same in these different areas. So I'll give you a kind of an idea of first kind of obvious cases, or like in topology, you often study invariants of things like three manifolds or knots. So I'm going to focus on 3 dimensions. And certain natural questions are what are the natural homological invariants of these objects. And we know that we can get a lot of insight into this from studying physics, dating back to work of Witten studying Chern-Simons theory in 3 dimensions. So this has some connection, physics of gauge theories, and specifically Chern-Simons theory. And it turns out that that objects that you might want to compute in Chern-Simons theory, like just the value of the Chern-Simons path integral on a 3-manifold, which is known as WRT invariants for gauge group SU2, are related to objects which arise in number theory. So usually these things are defined for Q being at a root of unity, but you could take the Q variable more seriously and consider them as functions which have some Q expansion, where when you specialize Q to e to the 2 pi I over K, where K is roughly the Chern-Simons level, you get the WRT invariance. But here in number theory, we like to study Q series. And what arises naturally are often things called Mach or quantum modular forms. So I'm hoping that at the end of today, you'll leave with an idea of the broader contexts, not just in three-manifold topology, but within physics or number theory more generally, of what these objects are and why they're interesting to study. And maybe something useful, maybe you'll learn something useful about them that you can take with you in whatever you're studying. So I would say one of the biggest questions, most interesting questions related to these things, we actually end up knowing a lot about Mach modular forms right now, and hopefully I'll give you a sense of how much we do know about them. But I would say a big question that's still open is why are quantum modular forms natural, and what's the true nature? How can you properly define or describe them? So you'll see when I actually introduce them, there's not really a formal definition. So. And we'll see that these kinds of functions arise from physics in a number of ways. And most of them are related to various BPS quantities in various theories. Okay, so the idea is that I'm going to focus on the kind of the number theory part of this triangle today. And I'll give you a rough outline of the things. So what I'm going to do is I'm going to introduce various objects in number theory, and along the way, I'm going to point out where they appear in physics or topology, and how some of their modularity properties can be interpreted from a physical perspective. So I'll give you an outline for the kind of objects I'm going to introduce. But the point is that I'll make comments along the way about why these are important, and hopefully you'll ask questions as well along the way, if you have any. So the first, starting with the simplest idea, are going to be objects which are naturally described by irreducible representations of the modular group. Which are often called Weil representations. And these objects are related to things which are probably very familiar, unary theta functions, which form a vector-valued representation of FL2Z, and other slightly perhaps less familiar objects, which are called false or partial theta functions, which are not modular at all in any way. But nevertheless, they have a very intimate connection to very familiar traditional modular functions or forms. Then, getting sort of less modular, I'll introduce Mach modular forms. And these, I guess, first kind of arose with a letter by Ramanujan about 100 years ago, where he kind of wrote down a bunch of functions that he called Mach theta functions. And he didn't really say what the definition was. He didn't prove anything about their properties, but he kind of wrote down a bunch of their properties, which all turned out to be correct. And he said that unlike these false theta functions, these Mach theta functions seem to have a very natural role in number theory. So we'll get some idea. Now, 100 years later, their properties have been understood rigorously, and we'll get some idea of how they appear in various contexts. And finally, kind of the most mysterious item on the list are quantum modular forms. Which, in their most exotic case, can be very strange, because most generally these are only defined, so these things are naturally defined for a complex number tau which lives in the upper half plane. These things are only defined on rational numbers. And there are examples of these that, in fact, don't converge in any open set of C anywhere. They only converge at isolated points, which is very strange. And they have some kind of modularity property. Or let's say like modified modularity properties on the rationals, which is kind of like similar to the modified modularity properties that we'll see when we talk about modular forms. And so the goal is that I'll describe these things and point out how they arise in physics and other areas of math. Okay. Are there any questions yet? I haven't really said anything. Okay, so let me start with one. So I want to describe a set of ideas which are all kind of related and are based on basically vector-valued representations of the modular group. So the representations we're going to consider are known as the Weil representation. And the idea is that the Weil representation is a vector-valued representation of SL2Z, or in the case of half integer weight, it's metaplectic double clever, but I'm going to never write that. Which is associated to a positive definite lattice. And I want to just consider the simplest case, which leads to unary theta functions, which you've probably seen before. And the simplest case is lattices of rank 1. So for rank 1 lattices, we can associate a representation, we can associate an integer m in a quadratic form. So we'll label them by an integer m and quadratic form, which takes elements from z mod 2m to the rationals mod z and maps an element x to x squared over 4m. So with this, we can construct a vector-valued representation of SL2Z, which is produced by the normal theta functions that you're familiar with. So the Weil rep can be written as a vector, which I'll call theta sub m, which has components labeled by r in z mod 2m, And the definition of theta mr is given by a sum over L equals R mod 2m of q to the L squared over 4m y to the L. And here we're going to let q equals e to the 2 pi I over tau, y e to the 2 pi I over z, tau be in the upper half plane, and z a complex number. And these functions have nice modular transformation properties. Which are given by 2m by 2m dimensional matrices S and T. Which I'll write for you.
So here it looks like Q is outside the unit circle. Doesn't that lead to a divergent sum?
Q is what? Sorry, I didn't hear you.
Outside the unit circle.
The unit circle. In the disk.
Did we eat the 2 pi times
Did you
tau
mean
or
2
minus?
pi I tau?
Oh, sorry. What am I doing? Good point. No, that's terrible. No, I would never want to do that.
Thanks.
I was getting ahead. I was thinking about modular transformations already, but yeah. Okay. So, no, we want Q to be in the disk, as usual, and tau in the upper half plane. Okay, so the modular transformation properties are given by these S and T matrices, which explicitly have the form, the following form. So now I'm going to use this number theory notation where E of x is e to the 2 pi I x, and T, R prime, is diagonal matrix. And these theta functions appear quite often when you study, for example, Jacobi forms, because they form if you want to expand, these have natural transformation properties, like Jacobi forms do. So you can always expand Jacobi forms of index m into a basis where the basis elements are given by these theta mr. So these form a basis for expansion of Jacobi forms of weight k and index m. So you can write a Jacobi form phi km of tau and z as a vector valued modular form f dot these theta functions, where f is a weight k, vector valued. I'm going to put VVMF for vector valued modular form. So these are things we're super familiar with. And in general, these representations, they're 2m dimensional vectors, and except when m equals 1, they're reducible. So in general, And so I want to talk a little bit about the classification of irreducible representations, subrepresentations of these 2m-dimensional Weil representations. Because these will appear again later in many places. Okay, so I'll give you kind of a sketch of how you can classify the irreducible representations. So one way is we'll start with a fixed m, and there turns out to be a natural action of the orthogonal group which I'll call O sub m, which is defined as the group of all elements A in Z mod 2m such that A squared equals 1 mod 4m. And this action on the theta function takes theta mr to theta of m A times r. And this action also commutes with the action of SL2Z. So and it turns out, but I want to make this kind of short, that there's an isomorphism, group isomorphism, between this orthogonal group OM and what I'll call XM, the group of exact divisors of M. And the group of exact divisors is, so n is an exact divisor of m if n divides m and n and m over n have no common divisors besides 1. And the idea is that we'll label irreducible subrepresentations by certain subgroups of the group of exact divisors. And the way that we can find the irreducible representations is by finding simultaneous eigenspaces of SL2Z and elements of, and the action of elements of this orthogonal group.
Excuse me.
Yeah.
I have a basic question. What is redundance? A squared equals 1 times 4m?
Oh, this is mod.
Ah, okay.
Yeah.
Thanks.
Okay, and then the group multiplication law between exact divisors, so the group operation star is such that n star n prime is n prime for this thing squared, and you can convince yourself that this thing forms the group. So the idea is we'll consider subgroups of the, so the idea, which I won't go through in detail, is consider subgroups of the group of exact divisors and find their simultaneous eigenspaces within the eigen space of SL2C. So for certain groups, one gets an irreducible representation. So I'll tell you one specific set of subgroups of exact divisors such that the corresponding representation is irreducible. And this will be relevant to modular forms of weight 1/2. So you can consider modular forms of different weight, and then you'll naturally get different subgroups which lead to irreducible representations. So we'll label our sub-representations in the following way. There'll be a vector-valued function, which I'll call theta m plus k. We're starting with this value m, and k is a subgroup of the group of exact divisors of m. And we're going to exclude m itself from being in this subgroup. And we'll, for some notation which dates back to number theory, is that if k is your subgroup of exact divisors, we'll write m plus k as m plus n prime, etc. And the conclusion is that theta m plus k is an irrep if the group of exact divisors is reproduced by the union of your subgroup and m. And also a caveat is also that m itself is square free. So you have to do something slightly more complicated if m isn't square free, but I won't go into that. So the idea is that we get irreducible Weil representations labeled by this index m corresponding to different choices of groups of exact divisors of m. So this perspective turns out to be quite useful, and I'll just give you one example so you get the idea. So an example is m equals 6. The exact divisors are just 1, 2, 3, and 6. And there are two subgroups which lead to irreducible representations. So this equals, you reproduce the whole group for either the subgroup k given by 1 and 2, or k given by 1 and 3. And this is because 6 times 2 within the group is equal to 3, and 6 times 3 equals 2. And for the choice of k being 1 and 3, we get an irreducible representation, which I'll call theta 6 plus 3, which has components theta 1 given by a linear combination of a bunch of the components of the reducible representation. So this thing is two-dimensional. And this two-dimensional representation has a T matrix given by this diagonal matrix and an S matrix given by this thing. Question? Okay, so this was very basic. But from these irreducible representations, there are a lot of different modular forms, almost modular forms that you can build. So the simplest examples are the weight 1/2 and weight 3/2 unary theta functions. So the weight 1/2 one, I'll call theta 0 mr of tau, which is the following sum. Now we've gotten rid of the y variable. And a weight 3/2 guy, which I'll call theta superscript 1, which you can write as a derivative acting on theta mr of tau and z, and then setting z equals to 0. And this is a similar sum. Where now we have as coefficient this L here. So this is weight 3/2. And the first thing I want to introduce that you probably might not be familiar with is what's called a false theta function. So to these functions, we can associate another Q series, which has no modularity properties whatsoever. And I'll call this a holomorphic Eichler integral. And this thing, well, I'll define it in general. So we'll let G be a weight W cusp form, which these unary theta series happen to be. with a Q expansion given by a sum of some coefficients, I'll call A sub g of n, q to the n. The holomorphic Eichler integral is, I'll call g tilde. So this is holomorphic Eichler integral. And this thing is defined directly in terms of the coefficients in the original expansion of g. So this is a sum for n greater than 0 of n to the 1 minus w times the original coefficient times q to the n. So this thing is not modular. And in the specific case, for example, for this weight 3/2 unary theta series, we get a function which I'll call psi which is this funny looking lattice sum where now the coefficients depend on the sign of L, which is what is spoiling the modular properties. And this thing, this psi, is commonly called a false theta function. So this function is holomorphic in the upper half plane with a very nice Q series expansion, but it's not modular. And in fact, this function itself looks almost exactly like this weight half unary theta function, but it's just that these signs here in the coefficients spoil the modular properties.
So can you explain a bit more how these are related?
This is related to this, or how it's
Now, how the definition, okay, why this is an integral?
Yeah, so it hasn't.
How the integral works out to be the sign of L in this case.
Yeah, we can talk about that a little later. It'll just take a bit too long, I think.
But what's the idea of this?
Yeah, so the idea is that you have an integral of something like, let's see, it's like tau plus tau prime to the 2 minus w. Let's call it g, tau prime, tau prime, tau prime, I infinity. I think it's something like this. Francesca?
Just tau.
Oh yeah, tau. Huh?
You have a branch cut, so it's at the denominator. The tau plus tau prime.
Oh, w minus 2, you mean?
Yeah.
Yeah. So yeah, you can prove that the integral is equal to this thing for certain weights. But
So is G a derivative of G tilde then?
is G a derivative of G tilde?
What's the inverse transformation, for example?
Let me think.
Yeah, it's a derivative.
Yeah.
I don't think of it as a primitive. But usually this way of thinking it, you do it for integer weights. And not integer weights, it's a bit more subtle to define the integral.
Yeah, that's why I avoided it, because we're in weight 1/2, so.
You can still do it, but then you have to do some integration by parts to make sense.
Yeah, so, yeah. Yeah, so because we're in weight 1/2, these integrals always have a branch cut or something like that. And then mathematicians actually often prefer to just define it this way. This thing matches easily for integer weight. Yeah. But we'll see a similar integral later on when we talk about modular forms. Yeah, but the origin of the name integral comes from this, but actually I would say most of the time in the literature you'll see this definition without any mention of this. Okay.
So it is not q to the power n squared, it is just q to the power n really, yeah, in g's, yeah?
No, it's
not a quadratic.
so. Yeah, so here I've, it is, well, here I did a variable change of n being like L squared over 2m.
But the sum over n is not the sum over squares.
Well, I'm just saying call the coefficients in this expansion.
I see.
Yeah. But it will be such a
There are
sum.
many zeros in this field.
Yeah, they're mostly 0. Yeah. But it's a little more convenient because then you can introduce this thing.
And this corresponds to omega equal to what? To
Omega.
1 to
Well,
psi
this
corresponds.
is general. Psi is when you start out with something that is weight 3/2.
So you start from.
So you have a square root in the denominator. But the idea is kind of doing this Eichler integral exchanges something of weight w with something of weight 2 minus w. So this thing is sometimes called a weight 1/2 false theta function because you started with something weight 3/2 and then you ended up with something weight 1/2. But it's not modular, so you shouldn't think of it as an actual weight of a modular form.
So how is the weight defined if it's not modular?
Well, that's just the weight is well defined. The weight of this g that you start with, or this g rather, is well defined. And then when you do integrals like this, often there's a duality in weights w and 2 minus w. So if you start with something weight 3/2, you can formally attach something weight 1/2. But it's better just to not talk about it in that way. Okay, so the idea is that, I'll kind of summarize, is just that false theta functions are homomorphic with nice Q series expansions, but no modular properties. Nevertheless, for each Weil representation, you can still associate a false theta function with it in this way. And now, at this point, I want to point out why you might care about these false theta functions. So you're probably pretty comfortable with the actually modular unary theta series, or Jacobi forms, things like this. But I'll just mention where these false theta functions arise. So I'll point out two ways in which they're notable. So the first one has to do with Chern-Simons theory on various kinds of three manifolds. And it turns out that if the manifolds are Seifert, then there's a very natural relation to false theta functions and their generalizations. And this goes back to Lawrence and Zagier. who considered the WRT invariance of the kind of the simple example of a Seifert 3 manifold, which is the integer homology sphere, the Poincare sphere. And what they notice, and there are many examples following this for other three-dimensional manifolds, and what they noticed is that that the certain false theta function, which I'll now label by a Bay representation, since you're now familiar with it. This form. So M is 30, and the group of exact divisors includes these numbers. Is finite in the radial limit and in fact it's the first component of this two-dimensional representation. So this is a two-dimensional SL2Z rep. It's finite in the radial limit, so as tau approaches a rational number in Q from inside the unit disk. And, so that's one. And secondly, when tau goes to 1 over k, it produces the WRT invariant of SU2 level K turns Simon's theory on the Poincare sphere, which I'll call sigma 235. And in fact, these numbers are related to the fact that the group of exact divisors is these numbers. 2 times 3 times 5 equals 30. And this thing, the fact that it has nice behavior at the rationals, is the first example of a quantum modularity property. A nice function that has some kind of modular properties at rational points. This is kind of nicer than the most general thing I mentioned earlier because, in fact, as I said, there are certain quantum modular forms which don't converge anywhere except rationals. This is a nice function which converges in the upper half plane. So it's kind of a sillier example of a quantum modular form, but nevertheless, it does have some nice properties at rationals. I'll get back to that later. So quantum.
Excuse me, I still wonder about psi.
Psi, yeah.
And why is it not 0? It is signum sine of L, yeah?
Yeah.
And times q to the power L squared.
Did I make a mistake?
No, just since it's a basic example, it would be positive, also. But then we can suppress sine, yeah?
What did I do wrong? I must have done something wrong.
Well, the condition R mod 2M isn't symmetric.
Oh, yeah. No. There are two ways of writing it. One is as a single sum. Yeah, sorry. Yeah, because we have this R mod 2M. It's not symmetric. So, yeah, you can write it as a single sum over all L in the integers with this sign here. Or you can write it as sum over L positive and separate out when L is R or when L is minus R. And for that reason, these things are also sometimes called partial theta functions because their sums over only half of a lattice.
I guess it'll be the case, for example, that when R is M, this thing will be 0.
Yeah, that's fine, but yeah. Yeah, so, R equals 0 and M never appear in the, they're always 0. Right. Yeah, thanks. Okay. And I want to mention one physics connection, which which kind of expands upon this observation, given a conjecture made by some people in the audience and people who are at this program previously. Who proposed a physical interpretation. So this thing has a nice Q-series expansion, and people have proposed a physical interpretation of this Q expansion. So I'm not going to spend much time talking about this, but several of the authors are here, so you can ask them more. And what they propose is that there's a natural, for all three manifolds, there's a natural decomposition of the WRT invariants into functions, which are, in the case of Seifert's false theta. And this decomposition goes something like the following. It's a sum over a billion flat connections on the manifold times some factors, which aren't really important, and certain S matrix acting on abelian connections. Times a set of functions which have a nice limit when you take Q to 1 over K. And these Z hats, which are labeled by abelian flat connections, are false theta functions, and they're generalizations. So generalization may mean including some linear combinations or some Eichler integrals of, for example, weight 3/2 functions as well for Seifert manifolds. And they propose that there's a physical interpretation, so as a certain index in a three-dimensional n equals 2 theory. So that would take another talk to talk about. But for people who are physicists and have heard about this, this is via a relation which has come to be known as the 3D correspondence, which relates a three-dimensional manifold with a three-dimensional n equals 2 theory.
And what is the role of SU2? Why it should be exactly 2? Or it's just known in this case, or there is a reason to restrict it?
Well, the WRT invariants are for SU2 level K. You can change this to a different gauge group. I mean, they made this conjecture as well. I think that you could change the gauge group and get the appropriate colored invariants for whatever gauge group you want.
And nothing will change in this false status, yeah?
No, the false thetas will certainly change to some other functions, which, yeah. So, so their generalization.
Now this is my question.
Yeah.
Where is the group in the false theta?
Yeah. So yeah, it's a bit of a more complicated story because there are many generalizations of false theta type functions, which you can write down. Some involve taking multiple Eichler integrals, like iterating them over, and you can imagine it roughly as when you have a higher rank gauge group, you have to account for a higher dimensional representation. You can also have different weights that you start with. You can take linear combinations of Eichler integrals of different weights. And so I would say the general story for what the relevant kind of functions are is not known.
Now, maybe I can ask you slightly differently. In your construction, which you described, so is there something related to symmetricity, the symmetric representations? Because from the point of view of group theory, SU2 is it's up only.
So your weight will change kind of whether the representation is symmetric or anti-symmetric as well. And so, let me think. Yeah, if you even just look at the expressions, you see that that one of these is symmetric and one of these is anti-symmetric under exchange of the lattice vector.
And somewhere also is this group K or whatever you call it.
Yeah, so I can tell you the things I think will be the same, that you can probably associate a Weil representation, but the actual functions which you get may be different. They may be more complicated. And so, I mean, the hope is one question you might wonder is how you can associate these irreducible representations with the properties of three manifolds or the gauge group or whatever. Let's say this is very largely unexplored. So hopefully, maybe some of you guys can try to answer these questions. But I think it's an interesting question. It's something we're working on. Generalization to higher rank gauge groups, different, more complicated manifolds.
But what happens is that just some false functions appear, in the description. It's senseless to ask which of them appear and why and what selects this particular one and so on.
It's senseless? I hope it's not.
You can enumerate these false functions as you explained. Okay, you can classify them. Mm-hmm. So, in the sense, what appears on the right-hand side has a kind of classification,
Yeah,
but maybe not all of them appear on the left-hand side,
That could be true. That I don't know. But I would say these false functions are kind of the zero level in a kind of tower of kind of more complicated functions, which are known as higher depth functions, which I don't want to talk about at all, because many of the concepts are the same. The fact that they converge in the upper half plane, the fact that they have nice limits as you go to rational points, the fact that they can be classified by Weil representations. These are kind of the important ideas which you can see already from the false theta functions example I gave. For these higher depth functions, many of that remains the same, but to define them is too complicated for this talk right now. But it's also something that people haven't explored concretely in many examples yet. But I think it's certainly a question and that I think is somewhat interesting and that probably someone should figure out. I want to give a second. I thought that I would be this slow. Okay, I want to give a second example of where false theta functions appear. So this will be a bit short. I won't say too much about it, but just so that you have an idea that it's not just that they pop up in this one place and that's it. So the second example is that false theta functions And again, the same story is going to hold. I'm going to give a particular example of where this specific kind of false theta function appear, but I expect that there are more complicated examples where generalizations also appear. But these specific kind of Eichler integrals of weight 3/2 theta series that I've written down here appear as characters in of modules of certain logarithmic conformal field theories. So I'll give you the name. These are singlet 1, P. Let me call them 1, M because it'll turn out that M is the same as the M that I've written down over here. Log CFTs. So one question is why, and I'm not going to answer like in very profoundly, but I can give you kind of an idea. So as I just pointed out, these false theta functions have this strange behavior. They're totally not modular. And well, what we're familiar with from rational CFTs is that there's a beautiful relation between vector-valued modular forms and the representation theory of rational conformal field theories. The characters form a vector-valued representation. The S matrix, control. I mean, there's a nice Verlinde formula which relates the S matrix with the characters and the conformal blocks. So in this case, we get something that's not modular for modules of logarithmic CFTs. And one kind of reason is, one idea of why you might expect this is that they have a more complicated representation theory than rational CFTs is, well, it all stems from the fact that the correlation functions of certain operators have logarithmic behavior. And this is related to the fact that the Hamiltonian L0 is not diagonalizable, it's block diagonalizable. And so there exist representations that are reducible. So they contain sub-representations, which are irreducible, but these representations are indecomposable, so you can't write them as a direct sum of a bunch of irreducible representations. So the representation theory is more complicated, and this, at a kind of vague level, is related to the loss of modularity of the characters. So the characters are not vector-valued modular forms. And in certain cases, like the singlet models, they have this behavior of false theta functions. But for other log CFTs, there are other ways that they lose modularity. So for certain cases, they're mock-modular forms. For other cases, they're generalizations of these kinds of things.
Can you say a few words about how these log CFTs are defined?
The singlet models?
Yeah.
Yeah. One second. So let me try to remember. You start with what's called a triplet model, which is usually written which is an extension of a Virasoro minimal model by 3 operators by some SL2, I think. Yeah, maybe I better not write it because I don't remember the exact dimension, the exact notation or coefficients. And then you
So what do you mean by extension?
Like you just have some, I think it's a SL2 current algebra at some level, which is three-dimensional. You know, it has three generators, and then to get the singlet, I think you take some kind of you take some orbifold, you gauge, and take some kind of diagonal. I can tell you more later. I didn't write it down, so I don't remember off the top of my head. But yeah, you start with this so-called triplet model. It has negative central charge. It's an extension of a minimal model, I believe, and then you do some orbifold to get what's called a singlet model.
But here you just get something like an infinite dimensional representation of modular group and nothing else. So
In which?
For logarithmic models. Not that you get just infinite triangular matrix. So when you transform it, you get not quite the original function, but a shift.
It's a general statement for log CFTs is I think we really don't know because they're not classified. But even for these cases, it's not something so simple as that.
Maybe I can make a couple of comments. So, to a question about the size, people don't know all the modules of log VOAs. I mean, classification of all modules in general is not done. But one can look at certain classes of modules, singled out by some conditions, and they give rise to finite size S and T matrices. And the answer to the previous question, what Sarah said is absolutely correct, but there is another way to define many log CFTs by analog of the familiar construction where we took a homology of some BRST operator. So that's a known construction of minimal models. But from that point of view, logarithmic VOAs, many of them can be constructed by taking not cohomology, but rather just kernel of screening operator. So you write free field representation, you take kernel of some screenings, and that always gives some logarithmic VOAs. That's a conceptual.
And what happens with modular properties? Something simple, yeah.
With modular property, not really. That's precisely, something quite complicated actually, and largely unexplored.
I mean, we don't even, without even knowing the full list of modules, it's not clear, what kind of, there's not something beautiful like the River-Linde formula that you can just write down in general for all log CFTs. You might, maybe some subset of modules do. There's some results for specific log CFTs where, if you add a set of functions which you call pseudo characters, then you can get something which transforms nicely under the modular group. But I don't think there's a systematic way to do that in general for general log CFT. Yeah.
So these Paul-seed functions, they have alternating signs. So what do you mean by characters? Like raise -1 to the inserted?
How are they defined?
So this is again related to the pseudo characters that Sarah mentioned. So these are what, she may correct me if I'm wrong, in modularity literature sometimes called twining characters. So this log VOAs have endomorphisms, and you may insert element of this end in the trace. So you're taking not just quite the trace, but trace of some element, G times Q to the L naught.
So this is some Z2 generator, some Z2 action?
It depends, but in simple cases it's Z2, but that's what gives rise to the sign. So it's actually...
But I think Pablo is asking even before that, if you just have the false without the pseudo characters, the false itself has negative signs in it.
Yeah, so it's a super trace.
Yeah,
so
but...
Then the next one, what happens if you don't, if you just calculate trace? What kind of function do you have?
I don't think it's, but these are bosonic, so I don't know what super trace means.
Well, super means that there is this endomorphism, that there is E2 somewhere. It can be formulated in purely bosonic language, but there is a E2 endomorphism, and insertion of that effectively gives rise to the sign. But anyway, that's a good question. I
Yeah.
think log VOA people didn't study what happens if you don't do that, because then you get even worse modular properties and they don't tell us what the result is.
So there's some, I mean, this kind of insertion gives you some cancellations. I mean, the function
Yes.
answer should be.
I think it's related to Alosha's question that in general it would be nice and desirable to have characters with all possible insertions for all possible modules. But this is very far from what log VOA people know. That's as far as I know.
As far, I mean, I'm not really an expert on this, but as far as I can tell from what I've been learning about log VOA, a lot is known about these triplet models. And almost as much is known about these singlet models, and then it's like some wild zoo of things where partial things are known, but not. Sorry, this isn't really addressing your question in any way, but just something I thought of. But beyond that, there are certain examples, like, I don't know, some free bosons or fermions with negative central charge, but more complicated ones, the idea of the scope, the classification, or for a particular log VOE, what the representation theory is not really known.
So I think it's like with the covariant TMF, this is one opportunity where physics can actually predict something that most people should expect.
So I want to point out, like, just the final comment about this is, given these two facts, these two ideas about where false theta functions appear, at least in certain cases of Seifert manifolds, there's a natural question which you might ask and try to explore more deeply, which is, can you associate more generally these two things? Is there a certain log CFT which you can attach to a three manifold in some way? Maybe there's a physical description which gives you some insight into this relation. So, I'd like to just
what
leave
is
it.
so special about logarithmic CFT from this point of view?
From this point of view.
Yeah. So now there are plenty of non-rational conformal theories. Yeah, logarithmic are not any special in this case.
Well, I think the idea is that there will be some attributes of this which makes this association natural, and like one thing you might think is, you know, Seifert fibered manifold. Like if you start with something simpler, like a Riemann surface times a circle, maybe not log CFT. Well, I don't know. Other people probably have an answer to this. And if you do something more complicated, like a hyperbolic three manifold, probably also not log CFT, probably something even more complicated. So I think it's a good question.
Yeah, I don't know the full answer, but maybe partial offer is that what makes them special is that their characters are not quite modular. And why this is important, it's actually easy to explain in the origin of this Z hat from physics. So it involves this combination of 3D analog of elliptic genus, which is modular, but it's contaminated by a three-dimensional piece. So in this 3D correspondence. And it's clear that any kind of three manifold that gives rise to non-trivial theory T of N3 will necessarily lead to such characters or Z hats which are not modular in the usual set. So therefore, there is no hope to find anything in the world of usual CFTs. So what makes log CFT special is that they have unusual modular properties.
Thanks. I'm just starting writing this definition because I want to say some level of detail about Mach modular forms, at least to give you an idea of how they fit in this story, and maybe just say a few words about quantum modular forms in hopefully 15 minutes, so we'll see. Okay. So a Mach modular form in the formal definition, and this was kind of explained about 15-ish years ago by Zwegers in his PhD thesis. He kind of gave a general formalism for understanding the context of Mach modular forms within number theory. It's a function, so I'm going to let MMF be Mach modular form, and F itself is our Mach modular form. It's a function on the upper half plane, which is holomorphic and is what I'll say almost modular, but almost modular in a very different way than the false theta functions are. And it's a function such that if you add to it this thing, G star, which is non-holomorphic, and I'll define that in a second, this F hat itself is modular. So the idea is that this thing is not modular, it's Mach, and F hat equals F hat of gamma tau times C tau plus D to the minus K for gamma in the modular group. And G is called the shadow of F. And G star is a so-called non-holomorphic Eichler integral, to be contrasted with the holomorphic Eichler integral, which gave us a false theta function earlier. And you'll see it has explicit dependence on tau bar. So this G star is defined as an actual integral. And again, you see a relation between the weight of the Mach modular form and the dual weight, which happens to be the weight of the shadow. So if F is, say, weight 1/2, then the shadow will be weight 3/2, and vice versa. So the general relation is that you have three functions, F hat, which is called the completion of the Mach modular form, F, which is the Mach modular form itself, and G star is the non-holomorphic Eichler integral of the shadow. And these three objects have the following property. So the completion is modular and non-holomorphic. And this thing is Mach, holomorphic, and nice, and it has a nice Q expansion. So the idea is that you're trading holomorphicity for modularity under this map. So I want to make some comments about where these things arise, and I actually have a much longer list of places that they arise than even false thetas, and I'll just say each one briefly, and I'll hopefully give you different perspectives of the role of Mach modular forms throughout math and physics. So
F hat doesn't have a nice Q expansion, or what?
F
hat?
No. So they arise in many places, and I'll try to give you a perspective of the nature in which they're arising. So I would say the first way they arise is more naturally algebraically. And an example is that they're characters of representations of certain CFTs are superconformal field theories. And what might be familiar to many physicists are, for example, half BPS characters of the n equals 2 or n equals 4 superconformal algebras in 2D. And you can kind of get an intuition for why you lose modularity in this case of half BPS characters. And roughly, when you consider these are basically short representations. And when you consider short representations, there are additional conditions. These representations are annihilated by certain supercharges in the algebra. And that means that there are additional null states in these short representations. And when you compute the character, you're basically subtracting off some of these null states, which usually, when they were there, would make the character modular. But now you're getting rid of some extra states, and you're kind of losing the modularity. A second way is, I would say, more analytic. And I won't say much about this, but Mach modular forms are also appear as the holomorphic part of what are called harmonic weak Moss forms. So these are functions annihilated by the hyperbolic Laplacian operator, functions on the upper half plane. A third way is geometric. And I'll give one example. So Mach modular forms, again, arise when you consider the elliptic genus of CFTs with a non-compact target space. And roughly the idea is, if you consider the way we usually define the elliptic genus, for a two-dimensional conformal field theory with some supersymmetry, this thing is, we usually have an argument that it's holomorphic, because for the right moving states, this doesn't appear for the ground states, and you're computing something that is just the Witten index. So the contribution of tau bar in this thing usually disappears, because when you compute the Witten index with target space of compact manifold, all of the excited bosonic and fermionic states come in pairs and they cancel out. But if you have a non-compact target space, that doesn't have to be true. And so in general, the elliptic genus will be non-holomorphic. And if you consider the holomorphic part, it's Mach modular. And this has to do also with the fact that the elliptic genus in non-compact CFTs roughly has contributions from a set of discrete states plus some integral over some continuous spectrum. And this is kind of like the decomposition into this Mach thing and this integral, which is non-holomorphic. And then finally, some other contexts in physics, which you may have heard of or not. Basically, anywhere you hear the term holomorphic anomaly, there is some kind of mock modularity which is going on. For example, topological string theory, Vathel-Witten theory on certain manifolds, like CP2. Yeah.
You also have some notion of quasi-modularity.
Yes. So that's kind of
often appears in this homology.
yeah.
But this is not.
What?
This is different, right?
It's a trivial. It's a.
Quasi-modularity.
Well, it's a almost trivial example of mock modularity where the shadow is a constant. So you can think of this all modular forms as mock modular forms. It's just that so regular modular forms have zero shadow. So they're sort of the most trivial case of mock modular forms. But something like E2 has a constant shadow. So the G star for E2, the second Eisenstein series, is E2 minus number over m tau. Something like this. So here our correction term is just a constant instead of an Eichler integral. But yeah, and this phenomenon is quasi-modularity. I would say it's kind of a dumb example of mock modular form. Okay, so let me think for 1 minute about what I want to say since it's been an hour and a half.
I guess the Vathel-Witten example is also the same as C because it's a M5.
Yeah. C.
I mean,
yeah.
The CFT equation is for the M5 ring reference.
It's related, yeah. I mean, yeah, you could think of it as a computation from a 4-dimensional perspective, or you could think of it as a 2D perspective. But yeah, I mean, the hope is that all of these things are not just totally unrelated, but they're kind of different perspectives on the same thing. And so the hope is that if you're someone who's very algebraic versus someone very geometric or more physicsy, that maybe knowing about these other contexts can give you some ideas about how to think about a more general picture. So I want to think for half a second of how I want to conclude, because obviously I had too much to say. Okay, so I will make some general statement about the connection between. You got kind of an idea of what a quantum modular form is, though I didn't define it. But that's kind of okay because there's no real definition. And I'll make some comment about the connection between these three things that I've introduced: false theta functions, mock modular forms, and quantum modular forms, and then I'll conclude.
But did quantum already appear?
Quantum appeared secretly when I talked about false theta function. Is it here? Yeah. I think I literally just erased it. Yeah, so, oh no. So I said that false theta function has a nice converges at rational points. And it has some nice, if you consider the function just restricted to the rational points, it has some modified modular property, which is like quantum modular property. So let me just say, a quantum modular form, in words, is a function on rationals such that if we define the following function to be sort of the difference between the original quantum modular form and its modular transformation, this thing is called the period function, and it has some nice property of analyticity or continuity, which you can extend to the real line. And this was originally, this notion was originally introduced by Don Zagier, and he purposely left the definition vague because he basically listed a bunch of examples where this period function sort of measures the loss of modularity. When you do a modular transformation on this function at rational points. And this period function has some kind of nice properties which you can extend to the real line.
Sorry, who is rational? Which variable is rational?
X. I guess I should really say Cx plus t.
X was tau.
X used to be tau, but now it's x. So in the false case, if you just take the limit as tau goes to a rational point, then tau becomes x. So
But tau is complex.
Yeah, so tau was x plus it or something. Now
both are rational. X is real.
But there exist such functions where you never had something in the upper half plane, where you really can only make sense of it at x.
But t can be arbitrary. Imaginary part.
Yeah.
So t is real and
Yeah.
real positive.
Yeah. So. So I'm going to make a couple general statements to conclude.
So here quantum is, again, the term quantum refers to what? I mean, is there a classical limit?
No, it has.
I think it comes,
It's
well, you know better maybe. I think it comes from the fact that in the original study of the invariants of the WRT invariants, there was, actually he has a whole page at the beginning of the paper explaining why he used the word quantum. I think it has to do with the fact that the original, like some of his simple examples come from the WRT invariants.
The examples are like Jones polynomials, the trefoil figure
Yeah.
8.
No, and the Poincare sphere is one of them.
That's totally true.
Right? But doesn't he have, he has two
quantum
reasons.
invariants.
Yeah, because quantum
There's
field
another-
theory. He has two reasons, right?
The other reason was just that it's supported on these points, which are sort of quantized.
Okay.
Well,
Yeah,
but
so
I mean,
that's more of a real reason. So it's not so much that it did come, some examples came from quantum topology, but the real reason is that in the world of modular forms, it fits nowhere basically, and it's defined on discrete points and so
Right.
well, I don't know. I mean, you Q it. The point is that this period extends to all of R, right? Is that the
No,
point?
not always. Not for all the examples of quantum modular.
No,
Yeah.
I thought that was the definition she just wrote.
no.
No, the period function can sometimes extend to some.
Now, what's it? Sorry, what was this definition you wrote? Can you repeat? I thought it was that the period function extended to R.
It can extend to R minus some set of points. So it doesn't. Yeah. So yeah, it's
If there is no variable Q, like no one.
yeah.
Can you probably tell us
Just
this
call
three-point
capital.
example explicitly?
That I am not prepared to do.
Upper half plane does not come back for this period.
No,
What?
no, there is nothing enough.
There is no upper half plane.
No.
There could, yeah. So in its most general and exotic form, there's no upper half plane. I gave you a trivial example where you had these, well, not trivial, but you had these functions, false theta, which do converge in upper half plane, and the limits as you go to Q give you a quantum modular form. So this has stronger properties. But there exist other functions where the upper half plane goes away.
But what was wrong with this psi at irrational points? You gave this alternative sign example, yeah?
Yes?
Sine of L q to the power L squared.
Mm-hmm.
Why should I keep x rational there?
Well, I mean,
It converges everywhere. No?
I mean, we want to consider action of
The
a.
formula was only for unit disk,
Yeah.
inside the unit disk.
Yeah.
But then the statement that only at rational points the limit will exist.
The limit t goes to 0.
L goes to real number.
I don't. Can you repeat the question?
No, you gave this example,
Yeah.
Sine of L q to the power L squared.
Yes.
And I just wonder what is special about rational points there.
Well, that converges is one example. One very special thing. I don't think it converges at non-rational points. I mean, you're taking sums, like for rational points, you're like taking sums of a bunch of roots of unity, so there's hope that the thing would converge to something.
But even with plus it converges, yeah, everywhere.
With plus?
Or just an ordinary theta function. If I omit this sign,
It only converges in the unit disk.
No, I don't think ordinary theta functions converge on the unit circle.
on the unit circle, yeah, I see.
Yeah, sorry, I'm going back and forth between the unit circle and the real line, depending on whether I'm talking about Q or tau. So the last thing I want to say is that if we don't consider the more exotic quantum modular forms that don't converge anywhere except rationals, then, and we stick to some of these simpler cases like false theta functions, there seems to be a natural relation between false theta functions, which define a quantum modular form at the rational points, and certain Mach modular forms. And this relation comes by taking Q to Q inverse. So there seem to naturally be pairs of false theta functions and Mach modular forms which can define the same quantum modular form. And given all of the context that we've seen for false theta functions and for Mach modular forms, which I didn't talk about as much, you might wonder if these pairs have some deeper meaning in math or physics or whatever. And I'm happy to talk way more about this because I haven't really given you much more than some context for Mach modular forms and their definition, or even how these are related to quantum modular forms is more subtle than how the false theta functions are. So, I mean, what I want you to take away, because obviously it would take too long to explain, is that there's some way to associate a quantum modular form to both Mach modular forms and false theta functions, such that they reproduce the same one, and they're somehow related to this operation. And that brings up a ton of interesting questions, like what do these pairs mean physically? Do they have relation to vertex operator algebras? Do they have relation to three manifolds? And we have various ideas about this, and there are a lot of open questions. So I'll just stop here, and we can talk later if you have more questions.
And already quite a few questions.
Yeah,
but
sorry
maybe, that's fine.
taking
That's
so
our
long.
style. We have for an hour and a half, but maybe there are more. So
So is it correct to say that Q is a quantum modular form? It's some function from Q, defined on Q, which is equivariant with weight K. The amount by which it fails to be equivariant with weight K for the action of SL2Z on Q is a function which is then continuous, like extends to R. So
Not all of R, though. It will extend to R minus like points, minus
minus a finite
cusps, or cusps. I mean, it's really infinite if you consider the SL2Z orbit of a cusp, but like
sure, okay.
Maybe finite with respect to SL2Z.
But like what's smaller than Q or what?
But
Smaller than. I think it's just the set of cusps for the particular. Like if you did it for a congruent subgroup, it would be like the set of preimages of cusps.
yeah, preimages of cusps, or preimages of I infinity, which give you cusps on Q. But, yeah. Yeah, did I say something wrong, Francesca?
Might not be not all the cusps.
Yeah, I was just making sure. Like, it depends on there are different sets of, cusps depending on what your congruent subgroup is, and...
So usually the I infinity is the problematic one, but then the rest might be okay. But again, it depends on which kind of examples you're looking at.
Yeah.
But in this false theta example, it will be at least on a half line. At least on the positive half lines. For false.
Yeah. Let's say all the rational points that are where you can completely define the limits of the false.
But I
So
mean,
you define the
the difference with Q in model transform Q, it will be, you can analytically continue. It's a analytic function of half line.
I think you can also define it even more than half line.
Yeah, I think it's even better because you can extend you can extend it even into the. Yeah, you can extend it even in different directions away from the cusp, right?
I think you can analytically continue with some cut. I'm not sure where. The cut is going to be somewhere. I'm not sure.
I didn't hear the end of it.
I think you can analytically continue this difference to some plane with some cut.
Right. Yeah.
The cut, I'm not remembering. It's either on the left axis or it's kind of right.
Yeah, I don't know. I don't know right now. But I think it's better than the most generic case. Yeah.
Right. And did you tell us exact relation between f and psi, or I missed it all?
No, I didn't tell you because I didn't want to keep you here all.
But it exists, yeah.
Yeah, and it exists, and it exists in different ways, and and it's sometimes subtle, and I'd be very happy to talk about it later. I can't, yeah.
But just if I take any mock form, you can define a quantum mock form for it, or it is itself more quantum?
You can define a quantum form, but you might have to do by hand, do some subtraction. So the mock form, unlike the false, does not converge at all rational points. It diverges. It's proven that it diverges at some of them. And so you have to, by hand, kind of do some subtraction.
Additionally to this, you already subtracted this.
No,
star, but
but we're just sticking.
Else,
we're
right?
sticking with f. We want it to be holomorphic. So let's keep f. It's a good Q series. It doesn't converge at all rationals. It diverges at some. But you can always pick a finite set of modular forms, which are labeled by your specific rational point. And if it diverges at a specific rational point, you can always find a modular form that you can subtract from it such that it converges and you get a quantum modular.
It is not equivalent to modification of the shadow.
It's not equivalent. I don't think it's very systematically understood how to do this. Yeah. It's known that you can do this, and it's been worked out in a number of examples. It's proven that it will equal exactly what you get from the limit of the false theta function. You can always do that, but a systematic way is not known, and hopefully physical intuition will... Actually, there are multiple ways you can do it, because you can always add a cusp form, for example, which vanishes at the cusp. So we hope that physical input will give you some kind of preferred way to start with a mock modular form and get a quantum modular form. So, that's a question I'm happy to talk about more later. But
can I still repeat my question about trefoil? I don't need a formula, just what should you do in order to glue it to the story? So
was it like the Kohler-Jones polynomial? I don't really remember what his particular
What you
example.
do is do a surgery on trefoil, and you get some.
Oh, it's just a surgery 3-manifold?
I don't know what it is.
I don't know. Maybe Tudor?
I mean, so one way to produce this false theta function is to do a surgery on trefoil and calculate those z-hats.
Right. I'm not sure if that's the example Don had. I don't
What was
know.
the question?
No, don't. Yeah, no. What
I
was
thought
question?
the question was that
But the
Don
question was
had
that
an
you
example.
can do something with the trefoil and see
It
the.
was one way. I think the other way is to consider the complement.
Well, for instance, you can do all kinds of surgeries on trefoil. They're labeled by 2 integer numbers, which are co-prime. They said P over Q surgery on the trefoil. You get a 3-manifold, and each of these choices gives you some z-hats.
I doubt that was one of Don's original examples.
No,
I thought,
it's not.
yeah.
We're talking about modern day.
Yeah.
I think Don's was more like a Kashaev invariant.
Okay. Yeah.
You can, the Kashaev invariant can mess with the quantum model.
So once again, Kashaev polynomial is a quantum morpho.
Well, Kashaev invariant can be defined as a rational points.
It's an excellent talk.
Oh. Well, I'm glad that you got something out of it. Hopefully people learned something.
Well, on this note, let's thanks
Yeah.
again.